Okay, so all of this brings us to Legendre's equation because Legendre's equation is the classic equation that's solved using the power series method. So Legendre's equation is an equation of the following form, where it's a second order homogeneous equation. And it's an equation that describes a lot of physical systems in engineering and physics, often in problems of spherical coordinate systems that have azimuthal symmetry. So this is what the general equation looks like, and n is a parameter that changes depending on what the physics of the problem is. So n's a constant. We're going to leave it as a constant in this particular derivation for a while because it just kind of depends on what physical problem you're solving. So now if we want to put this in standard form, we want to divide by this coefficient 1 minus x squared. And what we want to do is we want to apply the power series method to solve this problem. So we'll have y as our typical power series expansion, its first derivative, and its second derivative. So when we make those substitutions, this first term contains second derivative of y, second term contains the first derivative of y, third term contains y, and then 1 minus x squared minus 2x and k, which we're letting be n times n minus 1. Those become our coefficients. And so the first thing that we do is we take this first term and we split it into two different expressions, one with the 1 and one with the x squared. So here's our first term multiplied by 1. Here's the term multiplied by x squared, and you'll notice that this m minus 2 power becomes an m because we multiplied by x squared, so the 2 and the minus 2 are going to cancel each other. And so now we have, once again, 4 terms. All of those are summation terms, and once again the goal is to try to get the powers of s to be the same. So the first thing that we want to do is let's work on the first term. So in the first term we replace n with s in all of the terms except the first term, but in the first term, because this is the m minus 2 power, and we want to play around with the indices of the sum and the powers of x, then we're going to replace, for that term, we'll let s be m minus 2. So notice that everywhere else we just got a direct replacement here with s for m, but in this first term of the sum we replaced s with m minus 2. So that makes this power go to x to the s, and this index on this sum run from 0 to infinity instead of 2 to infinity. Since you are shifting both the exponent and the indices on the sum, you're allowed to do that. You can actually prove to yourself that that works out okay. Okay, so now what we want to do is, because we have even powers of, or we have uniform powers of x, we can basically equate our coefficients. Let me go back and show you that equation again. So notice these are all powers of x to the s. Okay, and so we're going to equate coefficients for that, and when we do, we'll pull out these terms and then this term with this subscript. So let's come and look. So when you do that, here is our s plus 2 subscript. Here are our terms for our coefficients, and then here's our a to the s, and that's just solving that. That's collecting like terms for the a to the s and solving for a to the s plus 2, where s runs from 0 to infinity. And so notice that here this recursion relationship skips a term. So if you had an a sub 0 here, this term would be a sub 2. If you had an a sub 1 here, this term would be a sub 3. So you're basically going to get an even and an odd a, since the coefficients skip by 2. And so what that's going to do is that's going to give you a sum with even powers and a sum with odd powers. So if you let y1 be the expression that has even powers, then you'll have something that'll look like this, where your general solution has this coefficient a sub 0. So a sub 0 multiplies this whole thing in your general solution, and then your y2 is going to have coefficient a sub 1. It'll multiply this whole thing because there is no relationship between a0 and a1, because the recursion relationship skips an index. Once again, we expect this because this was a second order differential equation. So we're going to expect that we're going to have an unknown a sub 0 and a1. We're going to have two unknown coefficients that are determined by boundary conditions. Now all these other terms, see, this term would actually be a sub 2, but we don't have to write a sub 2 because there's a relationship between a2 and a0. This term would actually be a sub 3, but we don't have to write that term because there's a relationship between a3 and a1. So we have the two unknowns, a0 and a1, and then everybody else in the equation is just a function of the recursion relationship. Okay, so we can kind of look at this in an alternate way, and this set of slides comes from a Wikipedia source that actually comes from some physics materials that people collected. And basically what you can show is that Legendre's equation can be written in this way, where these p sub n's are defined as what we call Legendre polynomials. And the Legendre polynomials can be found here. So like the first Legendre polynomial P1, you would take 1/2, and then you would take the first derivative of x squared minus 1. P2, you would substitute n's in here for everything, and then follow the algorithm to find P2. So then Legendre's equation then is based on these Legendre polynomials. And the reason that this is interesting is that, and here's just a table. If you use that algorithm, here's a table of the generated Legendre polynomials that come from that generating function for p sub n. So the reason that this is interesting is that the Legendre polynomials represent something physical. So here's a plot of what they look like. If you plot them between -1 and 1, then you find that they all end at 1, and they all start at either 1 or -1, and they have the first two have this constant and linear behavior, and then you get these sort of oscillatory looking shapes. They're orthogonal functions, and we'll discuss a little more about orthogonal functions later in the semester when we talk about linear algebra. But it basically means that they don't overlap in any way. And that also means that you can use them as functions in a series expansion. And so the most common use of the Legendre polynomial is in an equation that defines potential. And there are two types of potentials, and they both effectively have the same definition. The gravity potential, or the coulombic or electrical potential due to a point charge. So the gravitational potential would be due to a point mass, and the coulombic potential would be the electric potential due to a point charge. And those basically can be written as an expansion of this 1 over x minus x prime. And so let me show you a picture that gives you a better picture of what the geometry is here. But it turns out that if you have this geometric picture and you write it in this way, that can be expressed as a sum of the Legendre polynomials. So here's the picture. So we have our point charge here located at distance a from the origin of some reference coordinate system. And then we have our observation point located a distance big R away from our point charge and a distance little r away from our origin. And so the potential then can be written as approximately 1 over big R. And big R is geometrically related to A and little r. And so we can write that as this expression, which we mentioned on the previous slide, is actually a sum over the Legendre polynomials. So the equation on the previous slide is rewritten to correspond to the variables in this figure, and this then is what your electric potential looks like. So the electric potential can be written as a sum of the polynomials. Now what's interesting is that each value of n represents a specific charge distribution. So for n equals 0, you would have a single point charge at the origin, and the potential is that of a point charge at the origin. For n equals 1, you'd have a dipole charge on the z-axis centered at the origin, and so on. So what the model says is that if you have some charge somewhere on the z-axis, you basically are modeling that as a weighted sum of the charge, the part of the potential that looks like a point charge, the part that looks like a dipole charge, and so on. Now, since electric fields obey superposition, then this means you could have a bunch of point charges all along the z-axis, and each one could be written, the field due to each one could be written as, or the potential due to each one could be written as this weighted sum. And then because the weighted sum, the only thing that's going to change for a different point charge is the coefficient, basically could find the potential due to a distribution of charges along the z-axis by summing together all these terms. Now, because this problem has azimuthal symmetry, once you get the solution in terms of theta and r, then you have a complete solution, because then you can wrap around the z-axis in the phi direction and the solution looks the same. So multipolar expansions, go back to the figure. It's one of those areas in field theory that you don't necessarily cover because the mathematics can get somewhat complicated. But what you're really saying is, for this particular charge distribution, there's a part of that that looks like it was a point charge centered at the origin. But clearly it's not. So there's also a part of it that looks like maybe there's a little dipole, plus and minus, centered at the origin. And then maybe there's, a quadrupole, plus minus, centered at the origin, and so on. So it's an expansion of different possible charge distribution potentials, and then the coefficients, the A's, or I'm sorry, not the A's, but the coefficients that show up with the polynomial expansion represent the contribution of that field, and they are related to little a, the distance you are away from the origin, and little r. Now notice that you have a over r to the k. So what does this mean? This means when a is small compared to r, so you're pretty far away, then that means basically these terms are going to die off pretty rapidly. So if a over r is small, then as you raise that to a power, it gets even smaller. Now physically, when a over r is small, the point charge is close to the origin. Because if you're really, really far away, this point and this point look about the same. So the point charge, if a over r gets small, that means this charge is essentially at the origin. So what that means is you would expect a big contribution from your first term compared to all your higher order terms. If you get closer to the charge, closer to the origin, this looks less and less like it's at the origin. In fact, there is a point where this model breaks down. Notice this approximate sign. Okay, the approximate sign means that r has to be significantly greater than a. In this class, for this series of lectures, you will have a project for this unit on differential equations. And your project will actually be to try to model this problem with the Legendre polynomials for a given value of a and little r. And part of what I'm interested in is if you now vary little r and look at different distances, at what point does this look like a point charge? At what point does it look like a point charge plus a dipole? And so on. What should happen is you should see the contribution of the higher order terms drop out as you get farther and farther away. And that's just because this distance compared to this distance begins to look very small. So that concludes really the homework portion of the materials in this course. You'll have some homework problems. For this particular lecture on Legendre polynomials, you'll focus on a project. It's one of the projects that you'll do for the course this semester. So anyway, that pretty much concludes the differential equations portion of the course. There are some materials on Bessel functions, which are an interesting extension of the power series solution. And so there will be 2 additional lectures. But as far as the material that you'll be responsible for on homework and projects, that material concludes here.